Hey Algebras, so for your warm-up today we're going to do a little quiz review, and here's the key. If you're feeling good, then you can go ahead and take the quiz, but maybe you might want to review a little bit. First of all, this graph comes right from your notes, so maybe you want to try to fill it in before or go back and read your notes and see if we match. So we're going to remember this here is going to be our vertex. And our vertex is going to be our maximum for a graph that's down like a frown, or our minimum for a graph that's up like a cup. At this vertex value is where we're going to have this y value is going to be this maximum. And this x value, remember this is our line of symmetry, this x value is going to be either the time that it hits the top, or whatever your input value is going to help you figure that out. So when they ask you is, what is the maximum height? What is the maximum cost? What is the maximum? That's always going to be a conversation about your vertex. We want to make sure that you're good with that. This guy here is always our y-intercept, and that's when I have over 0 and up or down, whatever y value. And this is always going to be our start when x is equal to 0. So on the quiz, this is where the frisbee is thrown off the mountain. Maybe this is where the person is holding the ball before he throws it. So at time 0 is where that y-intercept comes into play. All right, here's the biggies that we're caring about all the time is going to be our x-intercepts. And our x-intercepts, if it's negative, we don't really use these much because that negative x value isn't really something that we pay a lot of attention to, because primarily if we're talking about time or something, it doesn't apply much for what we do. We can't have 0 or negative time. When we're talking about our positive 0, this is the one we care. This usually is when does it hit the ground, whatever is happening, whether it hits the water or hits the ground. It's also telling you how long it's in the air. So if we want to know what the time was as this thing was happening, where does my story stop? This extra box, I want to make sure that you know what it's for. If you are asked how high something is at a specific time, what we can do is you can always graph a horizontal line, and that can tell you the time that something is at the height, or you can always plug in values. So when we're talking about these kinds of graphs, we're talking about where something is at the start, maybe how high off of the ground it is, when does it reach its maximum. My time is usually across my x, and my height is going to be across my, or measured by my y-axis, and then when does something hit the ground. Make sure that you are feeling good about Desmos. So make sure that you can open up that screen. Make sure you can enter in that equation on the left-hand side. And don't forget all the ways that we talked about adjusting your graph so you can see this whole graph. Your plus or minus key, zoom. You can drag it and shift it left, right. And then that shift and dragging over the axis is how you can change the scales to see the entire graph. All right, so I'm going to post a second video that's going to show this problem here, the local nursery, selling the trees, and the quadratic formula. I'm going to show that in just a second. We're going to try something different, so hang on, and we're going to pause. All right, so I've got Desmos open. I've entered in my equation. 0.00, did I get all my zeros in? Oh, I think I have one too many zeros. 001, there we go, n squared minus 3n plus 50. And again, I can't really see my graph, so what I'm going to do is I'm going to drag it over, but I want to see more of what's going on. So by pressing shift, it allows me to change this axis, and now I have a better view of what's happening with my graph. I can continue to change this, and I can see what's happening with my graph, because what I want to see is a couple key points. I primarily want to see where this starts, that's my y-axis. I want to see where this bottoms out, there's my vertex, and that's my minimum. So when it says in this function how many trees in stock will minimize the cost, 150 trees are going to be my minimum. And what will that minimum cost be? $27.50. All right, we'll show you the next quadratic when we talk about the height of the punted football, where x is the horizontal distance in feet. So we'll come over here and change that. And a hint from Tommy was to refresh the page. And if you refresh the page, then you're able to go ahead and reset and reload all of your axes and whatnots. All right, when we're entering in this next one, I know that my h is equal to negative 0.01x squared plus 1.18x plus 2. So again, I can't see that whole graph. So what I'm going to do is bring it down. I'm going to zoom out and then start monkeying with my axes. So if I tighten this in, there, now I can see my whole graph. And I can see my y-intercept, where this graph starts. I can see my maximum. And then I can see my 0, where this graph ends. So it says, was the maximum height of the punt. So at, let's see, was that 59 seconds? The height of the punted football. X is the horizontal distance in feet, and the point of impact, and then h is the height. So it goes this far over, so it's not 59 seconds, it's 59 feet out, and 36.81 feet up in the air. At what horizontal distance from the kicker will the ball land? And that's going to be this value here. Whoop, you can't really see, that's this value here, which is going to be 119. All right, so we're back onto our paper again. So when you entered this equation into Desmos, you ended up with a graph that looks something like this. And we were talking about our cost of our trees being estimated by determining the number of trees that I purchased. And what I cared about here is going to be minimizing the cost. And that happens when I have a certain number of trees. So 150 trees was my input for my vertex, and that minimal cost of $27.50 is going to be that cost. All right, then I had this function where we talk about the football, and what's interesting about this one is its horizontal distance compared to height. So there's no time factor in here. This is how far the ball goes, and this is going to be how high the ball goes. So we want to make sure that we read what we're talking about and what each of our axes represents. So this vertex here, this maximum height of our punt, is going to be over 59 and up 36.81 feet. At what horizontal distance will the ball land on the ground? This ground here is going to happen at, it was 119.67 is where my height is going to be 0. Okay? All right, so on the second page of this, we have this conversation about each of our different forms of our quadratic equations. Our standard form is going to be where I have y is equal to ax squared plus bx plus c. Our vertex form is always going to be where I have maybe a coefficient, an x minus h squared plus k. Remember that this is always naturally negative. And then our intercept form, y is equal to, sometimes I have an a here, but we call this x minus p and x minus q. And we can say that p and q are going to be our intercepts, but remember this a might play a role also. All right, let's talk about each of these different features and forms. So when we're talking about standard form, our a and our b and our c values are the ones that we enter into our quadratic and our vertex formulas. And I like to talk about them together because if I have x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, that's our quadratic. But guess what? Here is our vertex, negative b over 2a. So that comes from this quadratic formula. The last thing to make sure that we know is that c is always going to be our y-intercept in standard form. And that makes sense because when x is equal to 0, both of these zero out, and that's just going to leave us that c. Okay? Let's talk about vertex form. When we talk about vertex form, our h and k, remember this one is naturally negative, so our vertex is always going to be h and k. And then when we're looking here, that's always going to give us our minimum or our maximum point. This is also the form when we can talk about these transformations in terms of that vertex. So we can say that this moves to the right 3. We can say that this moves down 1. We can look to this a value to see if there's a stretch or compression or if it's negative. All right, coming over here to our intercept form. Again, this a is going to be a factor that's going to talk about stretches or compressions. But we can always take these two values and we can solve for my zeros by setting each of these equal to 0. So x minus 8 is equal to 0 is going to give me positive 8. X minus 2 is equal to 0 is going to give me positive 2. These are going to be where my graph crosses the x-axis. Again, they're naturally negative, so p and q are going to have values that may be opposite of their factors. Now, the interesting thing is we can also set each of these equal to 0 to solve. So if I take my function and make that equal to 0, I'm solving. If I make that equal to 0, I'm solving. If I make that equal to 0, I'm solving. The intercept form is the easiest place to find those x-intercepts, but I can also find them for these forms too. All right. We're not going to get too fancy into the sketches here because you can enter them into Desmos and very quickly see your minimums and maximums and which way that these graphs go and where they cross the axis. So I know, for example, this crosses the axis at 2 and 8, so I can easily say that this graph is up like a cup, like that. For this one, I know that its vertex is going to be to the right 1, 2, 3, and down 1. So we can go ahead and know that this graph is going to be like that. For our graph here, it's a little harder to determine the vertex, but I do know it's down like a frown, and I do know that it crosses my y-axis at 14. So I know that's going to be my case. Now, for each of these conversations about domains and range, anything can go in. So we don't need to look at the graph to see, because in a quadratic, anything can go in. We need to look at the graphs to see the range. Our increasing and decreasing intervals, we need this vertex to be able to see where the path changes. And our end behavior we can get just from looking at these rough sketches. As x approaches negative infinity and positive infinity in this graph, my end behavior is going to become further negative, because it's a decreasing, it's a negative graph. Here, as my x's get smaller and my x's get bigger, my output is going to be heading bigger and bigger towards infinity, because these match and go up. Same thing with here. As x approaches negative infinity, as x approaches positive infinity, my output for this graph is only getting bigger and bigger. The next thing we can answer for all three at the same time, they have different y-intercepts and zeros, they have different vertices, but every single one of these is a function. Every single one of these is continuous, and none of these is one-to-one. All right. So now we've covered as much as we can without diving in. Now we'll go ahead and we'll graph. I'm going to use my graphing calculator. You can use Desmos. And we'll take a look at what each graph looks like. The opposite of x squared minus 8x minus 14. So pause the video if you need to, so that you can see what Desmos says. So we were right about it being down like a frown, but guess what? This graph actually is over on this side of the axis, right? So if I want to know this vertex, let's try to check out that table of values and see if I can see that negative 4, 2 is going to be that high point of that graph. And I could have found that by putting my negative b over 2a from my a, b, and c values. An a value of negative 1, a b value of negative 8, and a c value of negative 14. So my range for this graph is going to be from negative infinity up to and including 2. My interval when I am increasing is from x values of negative infinity up to 4. My decreasing intervals is going to be from that negative 4 when I cross over and I start going down. My y-intercept is when 0 goes in, so that's going to be negative 14. And my zeros for this graph do not look like they're right on. So in Desmos, you can go ahead and just click on those and find those values. It takes me longer with the graphing calculator because I need to put my cursor to the left and to the right. So my first 0 is negative 5.41. And my second 0 is going to be negative 2.59. My vertex I had at negative 4, 2, and I think I'm good for this first graph. All right, let's finish out this vertex form. We'll go here, clear, and we'll say x minus 3 squared minus 1. And we'll go ahead and look at a graph of it. How do we do with our picture? We did better on this one, didn't we? So our actual graph is maybe a little bit closer to the axis, right? If I look there. My range. I guess we should find our vertex first. So when I use my calculator, my vertex, I'm able to see that middle value, 3, negative 1. So, and of course we had it up here, over 3 down 1 for our vertex. Over 3 down 1, which means our range, our output values are going to be everything from negative 1 up to infinity. My increasing interval is going to be from 3 to infinity as my graph goes up, and my decreasing interval, negative infinity up to 3. Y-intercept, I can find that when 0 goes in, 8 comes out. And this one's pretty cool. I can see both of my zeros there, 2 and 4. So 2 goes in, 0 comes out, 4 goes in, 0 comes out. All right, last one. Let's look at our intercept form. And yep, you can enter this into Desmos or the graphing calculator too. So we can say x minus 8 times x minus 2. I can take a look at the graph. Let's see how we did here. Not too bad, right? Let's see if we can find our vertex. So, oh boy. Well, we have our zeros are going to be 8 and 2. Oh, I'm going the wrong way. 8 and 2. So there we go. And our vertex is going to be 5, negative 9. So our range is going to be from negative 9 up to positive infinity. Our increasing interval starts here with this 5 and goes up to infinity. Our decreasing interval starts at negative infinity, and that change happens at 5. Our y-intercept, when 0 goes in, I can get that from my graph. 16 comes out. Here's the best part. The zeros are given to us here. 8 goes in, 0 comes out. 2 goes in, 0 comes out. My vertex was 5, negative 9. So think about how much information we were able to get without Desmos just from those equations. All right, one last little bitty part where it says write the quadratic equation with this zeros and this vertex. And we're going to count on our vertex and our intercept form to help us out with that. So if y is equal to a times x minus p and x minus q, if we have these zeros, I want you to pay careful attention to how we do this. If x is equal to 4, then I know that x minus 4 is equal to 0. What did I just do? Subtract 4 from each side. So you unsolve for x. If x is equal to negative 3, that means that x plus 3 was equal to 0. So when I go to put these two factors into my equation, I have to remember that this A value might have changed my stretch or compression, so I have to keep that there in case I have a stretch or compression, because all I know is where this graph crosses my x-axis. All right, let's talk about vertex form. If I have vertex form, I have y is equal to some A value, x minus h squared plus k. So when I look at my equation, here are my h and k values. So y is equal to, I don't know about that A value, but I do know it's x minus negative 2, which is plus 2 squared, plus 6. Alrighty, good luck on your quiz.